Today we're going to look at logarithms. Logarithms were invented or discovered, depending on your point of view, about 400 years ago. They had a major impact on the development of mathematics and science. Logarithms, quite simply, are exponents. A logarithm of a number is the exponent to which you would raise some base to get that number. For example, if you look at 2 to the third power, that's equal to 8. You can rewrite this equation in this form. The log base 2 of 8 equals 3. Sort of brings the exponent down and gives it some kind of pride of place right there. And we say the logarithm base 2 of 8 is 3. 3 to the fifth power is 243. So you could rewrite that equation as log base 3 of 243 equals 5. 5 to the negative second power is 0.04, so you could rewrite that equation as the log with base 5 of 0.04 is negative 2. Okay, so these logarithmic equations are equivalent to these exponential equations. They're just two different ways of saying the same thing. And a lot of what you need to be able to do when you're working with logarithms is to translate from one form to the other, or perhaps in the other direction. Now here's a more general definition of logarithms. If x is positive and b is a positive constant not equal to 1, then y equals log base b of x if and only if b to the y power is equal to x. Again, if and only if means that these two statements are equivalent. Okay, so if you're given an equation like this, you could rewrite it in an exponential form. If you're given an equation in an exponential form like this, you could rewrite it in its equivalent log form. In this equation right here, y is the logarithm, b is the base, and x is what we call the argument of that expression right there, log base b of x. Logarithms have many useful properties. Most of these come from the properties of exponents. Okay, we're going to assume that r, s, and b are all greater than 0 and that b is not equal to 1. If you take the logarithm of a product, r times s, you can just rewrite that as the log of r plus the log of s. The log of a product is the sum of the logs of the factors. This also works for quotients, but not quite the same way. The quotient property says that the log of r divided by s is equal to the log of r minus the log of s. And these rules work for any base b that is positive and not equal to 1. The log of a quotient is the difference of the logs of the numerator and the denominator. A third rule that's useful is the power property. The log of a power, r to the k, is equal to k times the log of r. And again, b can be any legitimate base. And then a fourth rule is very useful, is the change of base rule. The log with base b of r is equal to the log of r divided by the log of b. I've written these with no subscript. That means this is a common logarithm and has a base of 10. When you're working with common logarithms, the base 10 is not generally written. So it's just understood that the base is 10 and we don't bother writing it. This is useful whenever you're working with logarithms on your calculator and you want to take the logarithm of a number. You want to take a logarithm of a number and the base is not equal to 10. In that situation, you use your change of base formula. Divide the log of the argument by the log of the base, and you're all set. Now what we're going to be doing with these logarithms is solving basic equations and transforming basic regression equations. And one skill you need to be able to do is to rewrite a logarithmic equation in exponential form or an exponential equation in logarithmic form. Okay, anytime you want to solve an exponential or log equation, you can always change it to the other form and you get your solution right away. For example, here we've got the log base 2 of x equals 5. If I want to solve this equation for x, I can just rewrite this as an exponential equation. I take the base 2 to the exponent 5 and set that equal to x. X equals 2 to the fifth. 2 to the fifth is 32. So we have this equation solved. Another one, log of x. Again, this is a common log because there's no base written here, so it's assumed to be 10. log of x equals 1.4. We can rewrite that as 10 to the 1.4 power equals x, just like that. And then we can go to our calculator and evaluate 10 to the 1.4, which is about 25.119. Common log of x equals 2.6. You can rewrite that as 10 to the 2.6 power equals x, and 10 to the 2.6 power is about 398.107, approximately. You can also solve exponential equations by translating them into logarithmic form. For instance, if you want to solve this equation, 10 to the x equals 1.7, just rewrite that as x equals the log with base 10 of 1.7. X is the common log of 1.7. You can look that up on your calculator. It's about 2.230. If 10 to the x equals 43, you can rewrite that equation as x equals the common log of 43, which is about 1.633. And then thirdly, if you have a different base other than 10, for instance, in this case 6, 6 to the x equals 12.5 can be written as x equals the log base 6 of 12.5. And then you can use your change of base formula, take the common log of 12.5 divided by the common log of 6. You can put that in your calculator, and it's approximately 1.410. So we're going to be working with logarithms a lot when we're working with scatter plots, trying to straighten scatter plots so that we can do best fit lines to those straightened scatter plots. And being able to translate back and forth between exponential form and logarithmic form will be an essential skill that you'll need.